So let me show some examples. So this is a very common examples in a naive basis. We want to detect the spam mails. So this is and we have a discrete data, and I'm using the multinomial naive and a naive base. So which corresponding to, as I said, it's on the categorical features. So that means my my XD here has the value from 1 to the K. Okay. So as I said, this is so the main setup. So the main setup is we start with some bunch of message. Some are normal message from your friends. Some are actually spam. This could be some like unwanted message that usually coming from the other ads or some other scan. So you can see right here, those red are marked as spam. Those blue are marked as a normal. So in total right here, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 of that is being normal. That 1, 2, 3, 4, 4 of that is being spam, right? So say that's our so examples right here. So see this is my so my training data set. So the question is we want to see if we got a message just starting with a dear friend. And we want to see whether it's classified as a normal or spam, right? So this is, so we got this like all these message and start with a dear friend. So we need to have two different equations, and one for is normal, another one is for the spam. So first thing that we need to do is we need to have some prior and probabilities, which is the probability of normal and compared to the probability of spam. That means it's if you don't have any like information, so what is the probability that the message is spam, and what is probability that the probability is normal? And here is, and since all the feature that I would assume is like an independent conditional on the label, so that means conditional it's a normal, and the probability to show as a dear and the probability to show as a friend, they are independent. So I actually can multiply them together. And this is basically the probability of seeing a word dear and a friend, given the message is normal, and this is the probability that seeing the word dear and a friend, given the message is spam. So and which one you give a larger value, we will give a score, and by the end of the day, it will give us the final and classifications. So, and how can we, and now the situation is slicing, we need to find out these probabilities, right? So this is the probability that we need to find right here. So, and what we do is we are trying to build a histogram of these 4 sentences shows up. So basically for the normals, and for the normal message, the dear shows up, and 1, 2, 3, 4, 5, 6, 7, 8, 8 of that. This is 8. This is 1, 2, 3, 4, 5. This is 3. This is 1. Then we normalize into probability, that the probability for given the n, dear shows up and with probability 0.47, and so on. So these are the 4 sentence and the 4 words, and it shows up. And say that's the only 4 words that it shows up in the messages. And if we start with the span, then we have 1, 2, 3, 4, 5, 6, 7. So then this is 2, this is 1, this is 0, this is 4. Okay, so then so from histogram we can calculate and conditional on so the message is spam, and what is probability to have a dear. And so as a compare And that means, so we can using all this information to actually calculate the probability right here. For example, this and right here probability, and dear given the n, that will be 0.47. The second one will be 0.28. And my prior here, it's 8/12. This is 4/12. So that means probability being normal is 0.67, and probability to be spent is 0.33. So that will be so the prior, then like multiply these two and the probability together, and we do the similar things for the span. And by the end of the day, we're getting the probability that that conditional on normal, the probability that show up and then you show up for the dear friend is 0.09. On the other hand, for the span, that would be 0.01. So at these cases, so because the score is, and for the normal 0.09, is much greater than the span of 0.01. So we will classify the dear friend as a normal message. So this is how we make the predictions. On the other hand, this message may have, and this method may have one big issue here. So the big issue is coming from if you see a message like this, money, 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 lunch. So say this is the message that you have, which could be a spam because it has a lot of money. Because from this histogram says if you, in the message there's a lot of money there, it's more likely to be a spam. So let's just calculate this probability right here. So this is the same and the same initial condition. Same like prior, which is 0.33 here. These are all very high, and 0.57 and 0.57. But by the end, you have a lunch that conditional on the span. In this case, is being 0. Then we have a problem, right? So once we multiply 0 and everything just goes to 0. So that means if you see a lunch right here, then you say, okay, there's no way, and this will be a spam because probability is actually equal to 0. So then as a result, we always like predict this is to be normal, but obviously this should be a spam in the common senses. So how can we solve these problems? So the reason of the root cause of this problem is because we have a missing data of the lunch right here. So we don't have any data for the lunch in the span and the span data like spam messages. So in fact, there's a very simple way to actually to solve this problem for these kind of missing data. You don't want to actually have this kind of situation in the practice, and just because you don't have any information for this missing data, and when you do the naive Bayesian, then you actually multiply and by 0, then the whole probability becomes 0 here. So what you can do is you can do something called add-one smoothing. There's also a name called Laplace smoothing here. So what you do is you add a pseudo count. That means give just an extra value to each word. So what we usually do is we just universally add 1 to each of the word counting. So this is, and this count is added to every word in both histogram. Even only one histogram has and one missing data. So this is to ensure you have all and roughly as much unbiased as possible. So you just universally add 1 count to each word. So in this cases you are getting 9. In this cases you are getting 6. In this case you're getting 4. In this case you're getting 2, 3, 2, 1, 5. So this is the key here. Previously you only have 0. Now it becomes 1. So after you do this pseudo count, then you are going to modify this probability a little bit because I mean, this probability will be changed accordingly. And the most important things, it actually changes for the launch and condition on span, which is 0.09 instead of I mean 0 right now. And of course, if you got this message, which is money, 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 money launch, that means if it is normal, then the probability is super, super tiny, which is 0.00001. On the other hand, conditional on being spanned, the probability will be 0.00122. So you can see it has a higher scores for span than the normal right here. So we will classify this as span. So here I call the score right here, but you can and of course you can normalize as well. So the way to normalize is you can actually calculate the posterior distributions by normalize it to be a probability. So previously here we have 0.09 and 0.01. You can divide by total of this. So as a result, if you see this x and theta and the condition on this features, the probability the y is being normal is 0.9. And on the other hand, the y equal to is being spanned has the probability of 0.1. So obviously, and 0.9 is bigger than 0.1. So we claim this is to be a normal and the normal as messages. On the other hand, so right here, so if we compare with this money launch, then the message tells me I'm actually this to be span is almost equal to 1 and versus to be a normal, which is almost close to 0. It's just because right here you have so many monies right here. It just and multiply them and together, and it has significant higher probabilities than the normal ones. But this is based on we have this at-one smoothing. If we don't do this, this probability is still being 0.0001, very close to it. But this probability will be precisely equal to 0. Something precisely equal to 0 cannot be compared with even a small but non-zero values. So as a result, then the probability will be completely flipped to be and probability 1 to be a normal message and 0 to be a spam message. But you can see this at-one smoothing can significantly alter the conclusions for this whether so this message is spam or normals. And this is particularly important for those missing data or very small data, because at-one and a pseudo count to those missing data can make significant contributions to our final posterior probabilities. Okay, here is another examples, and which is a Gaussian naive Bayesian and a Gaussian naive base. So this is some and also very interesting data here. We want to work with a continuous data. And for example, we have a measurement of popcorn, we have a measurement of soda, and we have a measurement of candy. So these are 3 consumptions taken from these 4 peoples who liked movie Troll 2. And I also take some and the data for 3 people who don't like and like the Troll 2. So these are the 2 and then the movies of Troll 2. But we are doing some statistics for 4 people who like it and the 3 people who don't like it. And what we actually do is we just plot the and that distributions with those samples that we already get, and we find out, and we calculate, and we're assuming this is from Gaussian distribution. So we only calculate the mean and the standard deviations for each data. For each features, and we just fit into Gaussian distributions. So we are going to using these curves to make some classifications. But you can see if we just using eyeballs, you can see from popcorns. So people who do not like the Troll 2 is consume the popcorn and significantly less compared to the people who like the Tro2s. And there will be overlap for the soda and the consumptions. But for the candies, it has significant large deviations from people who like it and from people who like it and from people who don't like it. So this like and behave and has shown like significant different behaviors for and for both groups. So what we do here, right here, is we are going to create a Gaussian, as I said, and for each features, which is the column of the training data. Then starting with the popcorn, and for those people who do not like the Tro2, we actually calculate mean and standard deviation. So for each group, we are going to, and for each group and for each features, we are going to calculate mean and standard deviations. So this, and for example, this will be mean of 4 and the standard deviation of 2. And for those who like the Tro2, and we're getting the mean of 24 and the standard deviation of 4, right? So, and this digit, so all you need to do is just to keep those and standard deviations and means right here. So you can and apply all these and fitting techniques to all the other features, including this is soda, this is candies. And you can see for here, we have, and this one, the mean is 2 and 220s, and this mean is 500, but standard deviation are being the same. For candy, this mean is 25, this means 100, but the standard deviation, this is 5. And the people who don't like it, that will be 20, right? So, say this is, and what you got for those like features. And also we need to calculate the prior, and I want to remind you, we have 4 people who like the Tro2, and the total we have 7 people. So total that's 4 out of 7 that people who like the Tro2, but so that would be about 0.0, and that would be about 0.7. And people who like do not like and Tro2 probability, the prior probability that someone doesn't like Tro2, that will be 0.4, right? So this is just give you some idea. And we have 4 people who like it and 3 people who don't like it. So and we can using this information, purely using this information to calculate the prior, prior distributions. Okay, so now if we have a new people show up who said they ate 20 grams of popcorn, 500 milliliters of soda pop, and 100 grams of candies. So these are actually features. Can we using this information to make a predictions whether this person likes Tro2 or not? And if you if you believe he likes Tro2, and we can send him some advertisement and target advertisement to encourage him to and to watch these movies. Okay, so if that's the information we got for this person, we actually want to calculate the probability. So basically, conditional that person really loves Tro2, that will be priors multiply the probability of popcorn equal to 20, and the conditional probability of soda pop equal to 500, and the conditional probability that candy equal to 100. So this is basically the likelihood, because for continuous variable, we don't have the actual probability. We only have the probability densities. So the issue is, if we actually multiply them together, particularly for the last one right here, you can see if this is my Gaussian here. So this is actually my Gaussian, and this is my my value right here. This is ended with super tiny numbers. This could be like 0.000 and multiple zeros and then 1. So this value is super close to 0. It might have a trouble when we do multiplications, because something is so tiny, and when we do this multiplication in the computer, it have a problem of underflows. So, and to avoid this kind of situation, instead of we just work with the multiplications of these 4 tiny probabilities, we are going to take the logarithm, and usually that will be a natural log with a base of e, and turning this multiplications into additions, which in this cases will be significantly convenient compared to the multiplications. So in this cases, we can see the first couple and the log of probability is quite large, but the last one is super tiny. It's a tiny numbers, but the logarithm of this super tiny number is minus 100 and 115. So think about how small of this value is an exponential minus 115. This is so close that you can't even like and express out in your own computers. Then we do the math, we find out the score will be minus 124. Then we do the similar things to calculate the scores for and doesn't like the troll2, and we multiply and we do the same trick. I mean, instead of we do the multiplications of the probability, we take the logarithm, then we sum them together. But in this case, we find out and the score is minus 48. And you can see for each component, they are quite small, but not as small as we had for this situation, which is so tiny in this like situation, and the minus and 115 here. So as this result, we find out the score of for doesn't love and doesn't like troll2 is significantly greater than score for like loves troll2. So as a result, we will classify this person as doesn't love like troll2. So this is how we actually make predictions for the continuous variables. In this continuous variable in a situation, we don't actually need to introduce add one smoothing, because I mean this is already continuous. I mean this is always smooth, and for like auto probability, it will be always bigger than 0, and we don't need to consider any like in a situation of the missing data that we had in the discrete and the data situations. Okay, so this is much more convenient, and all we need to do is just plug in this likelihood, probabilities, and we multiply them together. Okay, but we need to be careful. I mean, and because of the underflow problems, we cannot just multiply the likelihood together. Instead, we should take the logarithm of the likelihood, then we sum them together. So it will be much more manageable calculations than multiply these tiny numbers together. Okay. All right. So in the homework, you are going to work with something close to the first case right here. And also you need to implement this add one smoothing from scratch as well. And you're going to test everything on the MNIST data set to ensure you can and you understand all the concepts and the materials. I will provide a skeleton of the code that you're going to fill in each blocks, and then you can test on this test data set. And then you will see how good you have been performed. All right, so that's about everything I want to talk about for the naive Bayes examples. So this will be the end of this lecture. In the next lecture, we are going to summarize a little bit on what we already discussed on like current what we already learned on the classification algorithms. Okay, that's all.